Hi, and welcome to Chapter 6. In this chapter, we're going to continue talking about some important trig concepts, including ways to solve triangles that are not right triangles. We'll also investigate polar numbers in this chapter, as well as doing arithmetic with polar numbers and complex numbers in polar form. So there are lots of things involving trig in this chapter. However, today we're going to be talking about solving triangles using the law of sines. And some of you may remember that from your Algebra 2 class. If not, I would not worry, because we are going to do a thorough coverage of it in this class. So the deal today is that the law of sines works with any triangle. It doesn't matter if it's a right triangle. SOHCAHTOA limited to right triangles, but the law of sines works for any triangle. And what the law of sines says is that the relationship between the sine of an angle and the length of the side across from it, that ratio is the same throughout the triangle. So sine of angle A relates to the side across from it, side A, the same way that the sine of B relates to B, the same way that the sine of C, the third angle, relates to the side across from it. So this law of sines uses proportions. You can use the law of sines to find either a side or an angle, but it can only be used when you know one, and I call it this, angle-side pair. Okay? You have to know one angle and the side across from it. One angle-side pair. If we're going to solve this triangle, we are given a 29-degree angle here, a 112-degree angle here, and one side length. By the way, solving the triangle means finding all of the missing pieces. So we need to find the angle at T, the measure of T, and the measure of this side A across from the 112-degree angle. Alright, so let's begin with what's easy. I'm going to call up my calculators. Excuse me for a minute. And if we're going to find the measure of angle T, which I assume most of us would do first, that would be 180 less the two angles that we already know about, which are 29 and 112. So angle T is 39 degrees. To find the side lengths now, we turn to the law of sines. And we want to think about the angle-side pair that we know. And we know the angle at C and the length of the side across from it. So we're going to say the sine of 29 relates to 22 the same way, or will be in the same proportion, as the sine of 112 is to the side across from it, A. Now, if you remember your proportions, you know that we cross multiply, right? We multiply diagonally. So I want to just write this, and then I'll do the work in just a moment. But the sine of 29 times A will equal 22 times the sine of 112. To get A by itself, we divide by the sine of 29. So we need 22 times the sine of 112 divided by the sine of 29. Ladies and gentlemen, please make sure your calculator is in degree mode, because our angles are given in degrees here, and we can put that into our calculator just the way it looks. 22 times the sine of 112 divided by the sine of 29. I would just caution you to be careful about your parentheses. And it says here that the side A should be about 42.1 perhaps, and we didn't have a unit of measure on that thing. That sounds reasonable. You know, it's going to be, this side has to be the biggest one in the triangle since it's across from the biggest angle. We can find the measure of this side T. Folks, I don't want you to be fooled here. Please don't try and use the Pythagorean theorem. This is not a right triangle. So you need to just apply that law of sines again, using the angle-side pair that you know. Sine of 29 goes with 22, the same way that the sine of 39 goes with side T. And I'm going to just do the work, and I'll catch up with you. Okay, I did the arithmetic here. cross multiplied in the proportion, multiplied these two, and then divided by the sine of 29, and you can see that that's up here on my calculator. I ended up with about 28.6 units, which again is reasonable since this side A has to be the largest. Alright, so the law of sines, very easy to use. One of the issues, however, with the law of sines, sometimes when you're given the lengths of two sides and the angle that's not in between them, okay, we're given two sides and a non-included angle. Do you remember in geometry? Didn't you always want there to be the angle side-side postulate? This is why there's not one. When you're given a side, and an angle that's not included, folks, it's possible that more than one triangle can come out of that situation. Now, I've copied a table here from a textbook that we've used in the past, and it breaks this down really nicely. First of all, if we want to decide how many triangles are possible given a certain scenario, we should look to see whether the angle that we're given is acute or right or larger. So acute or not is basically what we're looking for here. And if the angle that we're given, the non-included angle, if that is acute, we next then look at the two side lengths that we were given. The one across from the angle is the one that we're comparing, and if the one across from the given angle is smaller than the other side length that you know, then there are three possibilities. If A is smaller than B times the sine of A, then there is no triangle possible. If, however, A is equal to B times the sine of A, then there is one solution possible. If A is greater than B times the sine of A, then it's possible that two triangles could be produced. And I love this graphic because it shows it exactly. That side A could be out here, or given that same side length, keeping it fixed, you can see that that piece A could fit here as well. So it could be that your A is a small angle in the triangle, or it could be that your side A is a bigger angle. So if we start out with an acute angle A, the angle that's given, and we have a side length A less than B, then it's possible for us to have 0, 1, or 2 solutions to our triangle. If, however, we start with an acute angle A and A is greater than or equal to B, only one solution is possible. The other case, the second case, is if A is not an acute angle. So we're given an angle that's not acute. Once you start looking at the sides, there are only two possibilities here. If the side across from your given angle is less than B, there can't be a solution, because you guys, if your angle A is greater than or equal to 90, it has to be the biggest side in the triangle. Therefore, it must be across from the biggest side. Biggest angle across from biggest side. So if you get an A less than B, then no triangle can be made there. If, on the other hand, A is greater than B, then there is one possible triangle. So that's a lot to remember, but I think that if we go through it step by step, keeping that table in mind, we'll see that it's not so hard to decide. Let's go on. We're going to try here 2 different times to decide how many solutions are possible for the triangle. And if you'll recall from the last page, the first thing you need to do is check the angle that you are given. Angle A is acute, so we are less than 90, and that puts us in the top half of that table. What has to be checked from there is the way that A relates to B times the sine of the angle. So we want to make this comparison. How does 18 relate to 25 times the sine of 63? And we can do the math here. 25 times sine of 63 is 22. That means that our 18 is less than 25 times the sine of 63. Now I think I remember that that means there is no solution, but I'm going to check. Yep, if A is less than B sine A, no solution. So there aren't any possible solutions in this scenario. Let's look at this one. We have an angle A that is obtuse. So we're in the bottom half of the chart on the other side. What we have to do next is check to make sure that the A side we're given is larger than the B side, and it is, because remember, the largest side has to be across from the biggest angle. One triangle is what will happen if we have an acute angle with A greater than B. Next, we're asked to find all the solutions for a triangle, and I'm going to just draw that triangle. This is not to scale, but I like to have something to look at. The angle that they give me, A, is 40 degrees. Across from it we have 54, and B, I don't know which angle we want to call B. I guess it doesn't really matter. The side across from it is 62. That makes this angle C. And okay, now we're ready to go. First of all, we're going to check to see how many solutions. We have an acute angle A, so we have to compare 54, see how that compares with 62 times the sine of 40. So 62 times sine 40, oh, 54 is bigger than. Alright, and again, I'm going from memory, but I believe that that means we're going to have two solutions. Yep, A is greater than B. We had an acute angle A with A greater than B sine A. So two solutions for this. Okay, so here's where we got to think. The law of sines will get us our solutions, so let's set up a law of sines for this thing. The sine of 40, that's our angle A, relates to the side across from it, 54, the same way that the sine of B will relate to the side across from it, 62. Doing the work here, we're going to multiply sine 40 times 62, sine 40 times 62, and then divide that by 54. Ooh, that's kind of weird, but it really isn't, folks. If you think about it, when you did this cross multiplying and then divided, you're solving for the sine of B. So what you're saying is that the sine of our angle B is equal to approximately 0.7380. Okay? To find a measure for angle B then, we have to do an inverse sine. So we're going to sine inverse 0.7380. And I'm using my answer function there. I have about 47.6 degrees. Around 47.6 degrees. Once we know the two angles, so this one is 47.6, we can add the two angles we know and subtract from 180 to find the measure of the third angle. And that's what I'm going to do. 180 minus 47.6 minus 40. That other angle C is around 92.4 degrees. And to find that length for side C, which is the only thing we have left, we can use the law of sines. So we go back to the angle side pair that we know. Sine of 40 relates to 54, the same way that the sine of 92.4 relates to the side across from it. So we want 54 times the sine of 92.4, and we want that divided by the sine of 40. Okay, I'm getting a C that is approximately 83.9 units, whatever those units are. And I think that makes sense. If C is the biggest, if C is the biggest angle in this triangle, then the longest side must be across from it. But, however, we said that there were two solutions. So I want to show you why there are two solutions, and I'm just going to draw your attention back to what we know about angles in the coordinate plane, folks. We've said that angle B is the angle whose sine is 0.7380. And that is an angle that goes somewhere like that. Okay, the deal is, in the first 180 degrees, there's another angle whose sine is that same thing, and it would be over here. This is the place where sine is also positive, and we could get that same height there. So there are two angles that have that as their sine. Okay, two angles have sine equal to 0.7380. And we only have talked about one of them. To find the other, we have to do 180, which would be all the way across here, minus that 47.6. So in our second triangle, okay, we're in our second triangle, the measure of its angle B is going to be 180 minus that 47.6 degrees. Again, I just want to point out to you, this is 47.6, so is that. They both have the same sign because their y values are the same, 0.7380. Okay. To find, go ahead and find that angle B here, 180 minus 47.6. Oh, that angle would be 132.4 degrees. Folks, that means that we're talking about an angle A of 40, but our angle B now has grown. Okay? This is angle B, this is A, this is 40. What you know in this triangle, this is 54. This angle B is now 132.4, and we already knew that this side was 62. It's this angle that's changed. Alright, finding the measure of angle C. We know two angles in the triangle. So let's do 180 minus 132.4 minus 40. That's 7.6. Ooh, that angle C is just a little sliver. The measure of angle C is around 7.6 degrees. Now we can use the law of sines to find that remaining side. So the sine of 40 relates to 54 the same way that the sine of 7.6 will relate to C. It's going to be very small this time. We want to multiply 54 times sine 7.6 and then divide by the sine of 40. And according to this calculation, our second triangle would have a value of C that was close to 11.1 units. Now if you think about that, C was a very small angle, so it should have a small side, and it is by far the smallest in this triangle. So all the solutions for a triangle given this information, there could be two. We found both of them. And I think the tricky thing is just remembering that once you know the angle B for your first triangle, you subtract from 180 to find the measure of angle B in the second triangle. Alright, and I'm sure we'll talk about that more in school. We've got one more little topic to discuss today that also uses the sine of a triangle. And I'd love to have you think about this. If we wanted to find the area of this triangle, I remember the formula says the area in a triangle is 1/2 its base, this length C, times its height, right? And the height just starts at a corner and hits at a right angle. So I'm going to use the variable r to stand for area. In this triangle, area would be 1/2 C times h. See, the deal is, however, folks, that h, we can find that if we knew some information about this triangle, okay? That is, if we knew even how long this side was and we had this angle, we could find that h, because we could use our SOHCAHTOA trig in this little right triangle and realize that the sine of angle A over there has to be h over b, and if we wanted to know a value for h, multiply both sides by b, h has to equal B times sine A. Well, that's very convenient. I'm going to put that in here in terms, instead of h, I'm going to use that b sine a and say that the area for a triangle can be found by taking 1/2. Let's look at what we'd have to have. We'd have to have a b side here and a c side here, b times c, times the sine of, and A is the included angle there, folks. It requires us to know that included angle. So if we know two sides in a triangle and the included angle, we can always find its area. That formula is going to be very helpful for us right there. Okay, let's see if we can apply it. Find the area of a triangle having two sides of lengths 8 and 12. So we've got a triangle out there that's got sides 8 and 12, not necessarily a right triangle. And an included angle of 135 degrees. Well, I didn't draw it to scale very well, did I? But I'm going to use that anyway. And it says that we should round our answer to the nearest square meter. According to our new area formula, we need to have 1/2 of the two sides that we know, 8 and 12. We need to multiply that by the sine of the included angle. That's the sine of that 135 degrees. And your calculator can do that for you in no time at all. 1/2 of 8 is 4. So 4 times 12 times the sine of 135 gives us an area of about 33.9 meters squared. So that's the end of our lesson today about the law of sines, and I'm hoping that you'll get out there and try that. You try as quickly as you can, and I'll see you in school.